Okay, so the kind of ending feature to the unit we've been on is using solutions to do stoichiometry. And you do that by using the molarity of the solutions. So, just a little bit of a review. We know that molarity is the concentration of solute in a substance, so how much, solid stuff is dissolved in there, and the solute is what does reacting. You get your molarity by dividing the moles per liter, but something I want to make sure we're clear about is what does it actually mean when you say you have a 6 molar solution of something? What that really means is for every 1 liter, you have 6 moles of the substance, because 6 moles divided by 1 liter would give you 6 molarity. Okay? If you have a 2 molar solution, it would be 2 moles per liter. If you had a 4.5 molar solution, it would be 4.5 moles per 1 liter of solution. Okay? That's an important distinction to make here. So, we don't usually work in liters, we usually work in much smaller amounts, like maybe 20 milliliters or something like that. Say you don't have an exact liter, say you have half a liter. If it's 6 moles per liter of solution, how many moles would be in half a liter? Okay. Should be pretty easy to come to the conclusion of 3 moles, but you can actually, especially for numbers that may not work out easily in our head, you can set something up like this. If I have 0.5 liters of solution, and I know my concentration is 6 moles over 1 liter, I don't need my duplicate ones. Alright, my liters cancel out, giving me 3 moles. Okay, I'd write this down because this setup is going to be important for our stoichiometry. Okay, so stoichiometry, when dealing with it with molarity, you'll see questions like this, but they're still going to be asking the same questions we dealt with before. How much of this product can you produce? How much of the other reactant do you need? If we make this much product, how much reactant must have been used? Stuff like that. So, just like before, you have to start by writing out your balanced equation. Alright? So based on reading here, it says you react 50 milliliters of 6 molar hydrochloric acid, so that's one of my reactants, with a solid piece of magnesium to make hydrogen gas. Think carefully about how to write that. Gotta remember it's diatomic. Plus magnesium chloride, but this is an ionic compound, so we need to remember this is -1, this is +2, so I'm actually going to need 2 of those chlorines. And then lastly, to balance, hydrogen and chlorine have more on the product end. If I put a 2 out here, it balances. Alright, so after you have your balanced reaction, the rest of the steps are very similar to what we did with stoichiometry. It's just sometimes it won't be a molar mass conversion, it's going to be a molarity conversion to get us to moles. So once we know we have our balanced and correct reaction to work with, we have to convert to moles in order to be allowed to use those molar ratios. Okay? So I have a concentration and a volume. I can convert that to moles, except it's coming out from the molarity equation, so you have to convert those milliliters to liters. So first I'm going to start by doing 50 milliliters divided by 1,000 milliliters per 1 liter gives me 0.05 liters. And once I have my volume in liters, that's when I can start my stoichiometry. So I'm going to have 0.05 liters, and this was of the hydrochloric acid. And then what I'm going to do is this step here, I'm going to use my molarity to convert this to moles. But it's going to look better if I split it up into that whole, since it's 6 molar, it's 6 moles HCl per 1 liter HCl. Then you can see that the liters of hydrochloric acid cancel out. and I'm going to be converting to moles. Okay. Now that I've converted to moles, I'm allowed to apply my molar ratio. Moles of hydrochloric acid have to go in the bottom so that I can cancel those out. And then the question is about the mass of magnesium chloride. So I'm going to put moles MgCl2 up top. Now, where do the numbers come from when you're dealing with the molar ratio? It's the only time you use these coefficients. Alright, so I'm going to put a 2 with the hydrochloric acid, and then since there's no number in front of the MgCl2, I'm going to put a 1. And there's my molar ratio. Last step, convert to grams. So molar mass is always equal to 1 mole, and I need to put that on the bottom to cancel things out. The molar mass of magnesium chloride is 95.21 grams MgCl2. So far I've canceled out moles of hydrochloric acid, moles of magnesium chloride, leaving me with grams of magnesium chloride. And when I calculate this out, I get 14.28 grams MgCl2. Okay. So, you try this one. Get your reaction set up, do your problem, convert the milliliters to liters, and then start off with your stoichiometry. This is set up very similarly to the last problem. So, pause the video, you try it on your own, and then watch the video and see if you match. Okay? So, starting with getting my reaction, I know I'm reacting KOH with calcium chloride. Alright, it's a double replacement, so now the K is going to be attached to chlorine, -1 + 1. Okay, and this was +2, -1, +1, -1. That's why the formulas are working out the way they are. And calcium is going to be attached to two hydroxides. That's +2 and -1. To balance, I'm going to need to double my chlorines and double my hydroxide and potassium, and now I'm balanced. Last thing, since the question is asking about our solid product, gotta look at those solubility rules. Potassium falls in group 1, so that's always going to be soluble, so our KCl is dissolvable, it's going to be aqueous, but hydroxide almost always forms a solid, and calcium's not one of those exceptions, so our solid's the calcium hydroxide. Alright, and then I need to convert my milliliters to liters. 0.45 liters, and now I can start my stoichiometry. So 0.45 liters, and then it says you react 450 milliliters of 0.45 molar potassium hydroxide. So that means that is about the potassium hydroxide. I need to use my molarity to convert to moles. So that's 0.45 moles per 1 liter. That's going to cancel out my liters. I need to be writing in my KOH. Next I can do my molar ratio. So I'm going to have moles KOH on the bottom. I want to go to my solid product, so I'm going to put moles calcium hydroxide up top. And then coefficients are a 2 for KOH and a 1 for calcium hydroxide. And last, I'm going to convert to mass. 1 mole calcium hydroxide, 74.096 grams calcium hydroxide, and that's going to be equal to 7.5 grams CaOH2. Okay, I can confirm that I set this up right when I cross things out, and everything cancels, leaving me with my grams of calcium hydroxide. So, last problem. This one is just another thing you might see, particularly when we get to our worksheet. Here we have the question, what volume of a 1.2 molar sodium hydroxide, and there needs to be the word solution in here, must be used to neutralize. That word means same thing as react completely. Okay, so if you see that, it just means you're going to use up all of your other thing. Okay. So to neutralize or react completely with 450 milliliters of 2.5 molar hydrochloric acid. So you're going to start by writing out your equation. Oops. So we have NaOH plus HCl, and I know it doesn't say it on here. Honestly, I more just want you to focus on the word neutralize and remember what that means, because your worksheet actually already gives you your equations, you just have to balance them. But this would be another double replacement reaction, so we'll make water and sodium chloride. This one also happens to work out balanced. If you're missing where the second hydrogen is, there's one in hydrogen chloride and one in sodium hydroxide, so that makes the two that are in the water. So let's convert our milliliters to liters. .45 liters, and now I can start. 0.45 liters is associated with the hydrochloric acid. Okay, and just like we've been doing so far, we're going to use molarity to convert to moles, because we are given a volume instead of a mass. So it's 2.5 moles per 1 liter. Alright, liter goes on the bottom because that's going to cancel out the liters that we started with. So liters are gone. Then molar ratio. Got my moles of hydrochloric acid, and where the question is about what volume of sodium hydroxide, so we're going to go to sodium hydroxide. Alright, and since this started out balanced, all of the coefficients are 1. And then the last step. This is going to be different than what we've seen before. So we're in moles of sodium hydroxide, and we want to know a volume. What's going to help us more here, a molar mass or a molarity? So since molarity has volume in its equation, molarity is what's going to be helpful here. So we're going to use a molarity again, but this time, where do the liters have to go? Are they going to still go on the bottom? Would that cancel out moles? Or are we going to put 1 liter on top and then our moles on the bottom? Hopefully you are saying that the 1 liter of the NaOH goes on top, and then the concentration of that solution was 1.2 molar, so we're going to put 1.2 moles of NaOH on the bottom. Okay, that's going to cancel those out. Math-wise, we'll do the 0.45 times 2.5 divided by 1.2, which gives you 0.93 liters. Actually, I think it rounds to 9.4 of our NaOH solution. Okay?